Hi class, we're starting chapter 5 on integrals, section 5.1, area and distance, part 1. So our first goal is to find the area under the curve. So find the area that is bounded by the function y equals f of x and the lines x equals a, x equals b, and the x-axis. So for example, we'd want to find this green shaded region, so the area under the function y equals f of x, bounded by the vertical lines x equals 0, x equals 4, and also the x-axis. So to calculate the exact area under the curve, we're going to start with approximations. So our first estimate will be what is called the left Riemann sum. So we can see from the picture that the left Riemann sum means that we're using the left endpoint of the sub. So these are our subintervals. So in this case, we have 4 subintervals. Use the left endpoint of the subinterval to get the height of the rectangle. The width of the rectangle, at least for now, are all the same. So we would simply add up the area of these rectangles, and that would give us an approximation of the area under the curve. The right Riemann sum is the same idea, but now we're using the right endpoints. For this particular function, we can see that using the right endpoints would lead to an overestimate of the area under the curve. We'll also be using the midpoint of each interval. So like we have here, the midpoint of this first subinterval is used to get the height of the rectangle. Okay, and so forth. For this picture, the midpoint does seem to be a better approximation because we can see that we're underestimating some of this area on the left, but then overestimating this area here on the right. So it looks like it could kind of even each other out. So the area that we're getting from adding up our rectangles seems like it would be a fairly good approximation for the area under the curve. And then also we see that if we could increase the number of rectangles, that would obviously give us a better estimate of the area under the curve. In this section, we're calculating the area by hand, so we'll limit ourselves to 4 or 6 rectangles. But then as we move on in the section, we will let the number of rectangles increase without bound, so go off to infinity. That'll be our limiting process. And then as we take that limit, we see that we end up with the exact area under the curve. Okay, and then also one other thing I wanted to mention is that eventually when we let two things, the number of rectangles needs to increase without bound, so that's going to go off to infinity, but also the width of the rectangles needs to get smaller and smaller. That is what is called the mesh size. So for example, if we look at the distance between x sub 3 and x sub 4, that needs to get smaller and smaller. So the distance between this is called our delta x, so the change in x. So the delta x needs to get smaller and smaller. And then we'll allow, so looking at this fourth subinterval, x sub 4 star is simply going to be any point that's within that subinterval. So it doesn't matter if we're choosing the left endpoint, the right endpoint, the midpoint, or any other point within the subinterval. As long as the subinterval is getting smaller and smaller, these 4 points that I have here are going to get closer and closer together until they're actually the exact same point. Okay, so that's why we'll switch to, basically it's just called like a sample point. So our x sub, in this case, x sub 4 star, again, just means any point within that fourth subinterval. All right, so example number 1, we are going to use 6 rectangles, so 6 subintervals, 6 rectangles to estimate the area under the curve. We will find L6, R6, and M6, so the left endpoint, the right endpoint, and the midpoint, all using 6 subintervals or 6 rectangles. Our function is given, so this time it's given as a graph. Other times in the homework, you'll actually be given the function. Okay, and we're going to go from -2 to 10. So on my graph, I'll mark off -2 and +10. Notice that, so again, it's called our delta x, or the change in x. In general, this is b minus a over n, where a is the start of your the beginning x value, b is your ending x value, and n is the number of subintervals. Okay, so in this case, we have 10 minus a negative 2 over 6, so 12 over 6, or 2. So each subinterval is going to be 2 units long. So your delta x is the width. That's the width of each rectangle. Okay, so we're going to need to calculate the height of the rectangle. We're going to start doing L sub 6 first, so using the left endpoints. So I need to evaluate f of negative 2. That'll be the height of the rectangle. And then I'll multiply that by 2, which is the width of the rectangle. And that would give me, so this marking right here, that is f of negative 2. Again, that's the height of the rectangle. Multiply it by 2, and that'll be the width of this. That'll be the area of that first rectangle right there. Good, we're going to then go to 0, so f of 0 times 2 plus f of positive 2 times 2 f of 4, f of 6, and finally f of 8. Okay, so again, the width of each subinterval is the same, so each rectangle is 2 units in width, so that's why I'm multiplying by 2 over and over again. The height of the rectangle is what's changing. So f of negative 2 is the height of the first rectangle. F of 0 is going to be the height of the second rectangle. So that looks like 9 right on my graph. And I can see this time it's going to give me an overestimate of the area under the curve. Next we would have f of 2. So again, another overestimate. F of 4. F of 6. And then finally f of 8. Okay, so again, we're approximating the area under the curve. So L sub 6 is our approximation using 6 rectangles or 6 subintervals. In this picture, we also need to estimate because you don't know the exact value of f of negative 2, for example, so you're just looking at the curve and coming up with your best approximation. Okay, so for that y value. Okay, if you were given the actual function, then you would just plug in negative 2 to the function and you would know that the height of that first rectangle. Okay, so again, you'll need to calculate the delta x, which again is the width of the rectangle, so b minus a over n. In our case, 10 minus a negative 2 over 6, so 2 units for each rectangle. And then L sub 6 is what I just talked about, so f of negative 2 is the height, 2 is the width. The second rectangle, f of 0 is the height, 2 is the width, and so on. These are the values I chose for f of negative 2, f of 0, f of 2, and so on. The width of everything was 2 units, so I came up with approximately 95.4 units. Okay, so next we'll move on to calculate r sub 6. So this is now the right endpoint. So this time I'm going to use f of 0 for the height of the first rectangle, and then I'm going the other direction, right? So f of 0 is the first height, f of 2 gives me the second height, and so forth, f of 4. Okay, so I finished drawing the picture. So R6, again, using the right endpoints. So this time we would start at f of 0 for that initial height. each rectangle is still 2 units long. So f of 0, f of 2, f of 4, f of 6, f of 8, and f of 10. Okay. Another thing is that I may have mentioned it in the last one where we were looking at the left endpoints. On the right endpoints, we can see that for most of these, using the right endpoint in this picture is giving us an underestimate. Okay, the exception is this first rectangle. 9 is an overestimate for the rectangle, for the height here. Our function is increasing on that section, but then it's decreasing. So where it's decreasing, we see that the right endpoint is giving us an underestimate of the area. Okay, so a couple things. So we can know ahead of time, oftentimes we can know ahead of time if our estimate will be an overestimate or an underestimate. And that's based on whether the function is increasing or decreasing, but it also has to do with the concavity. Okay, so here are those, the function values, and then I just approximated f of 0 is equal to 9. The other guys are approximated. Okay, so you might have slightly different answers there. This works out to be 85.9. All right, and now the midpoint. Okay, so again, we're going from -2, I'm going to draw a vertical line here, -2 to 10. So the first, my first interval is from -2 to 0. So conveniently, the midpoint is -1. Okay, so I would go over to f of -1 and use this for the height of that first rectangle. F of 1 is going to give me the height of the second rectangle, f of 3 for the third, and so forth. Okay, so I finished shading in the graph. F of -1 is the height of the first rectangle, so I'll multiply that by 2 to get the area. F of 1 is the height of the second rectangle, again times 2 for the area. F of 3 for the height of the third rectangle. F of 5 for the next one. F of 7, and finally F of 9. Okay, good. So again, we can see that for at least for this particular function, and I'll look at this last, maybe this last rectangle is a good example here. I see that I'm missing, if I'm comparing this to the actual area under the curve, I'm missing this portion up here, right? So that part I underestimated. However, I'm adding in this portion over here on the right side, which really shouldn't be there because that's not the area under the curve. So it looks on this picture that the midpoint approximation is going to be a pretty good approximation because with each subinterval, we're kind of balancing out some of it being an overestimate and some of it being an underestimate. Again, that doesn't mean that the midpoint is always the better approximation. It does depend on what the function looks like. Okay, so again, I estimated the values of the function at those points, added them up, I came up with 91.2. Okay, so then just to go over, these were our different approximations using the left endpoint, the right endpoint, and the midpoint. And based on the picture, it does seem like M6 is going to be the best approximation for the actual area under the curve.